In this lecture, we're going to be discussing three different things that all kind of come together in the next couple of weeks. But first of all, I'm going to be talking about z-scores, and then we'll be talking about the normal distribution, and finally we'll have an introduction to probability. All of these topics are, of course, covered in your textbook as well, although in a slightly different order. So be sure you also read the textbook for additional information. So the first part, I want to talk about z-scores, and I just want to apologize for a moment that you know that I'm an American, and sometimes I might slip and call it a z-score. So I hope it doesn't confuse you too much, but a z-score is American for z-score, so I might say that. But anyway, a z-score is what we're going to be talking about, and z-scores are an example of a transformation. And a transformation is a mathematical operation that you apply to every score in the data set. Now, some examples are that you could take any data that you have and subtract 1 from each of the scores so that everybody's been reduced by 1 point as a score in the data set. That would be an example of a transformation. Something else you might do, for whatever reason, is you could divide every score by 6. So you take each score divided by 6, or you can multiply each score by 3/4, and so on. Now, of the different mathematical operations you can perform on scores in a data set, a special class of these is this kind of transformation, a linear transformation. And what's good about a linear transformation is that when you perform the same transformation on every score in the data set, it doesn't change anything about the shape of the distribution. It just puts it on a different scale. So here's an example of this. Let's say there are 6 scores on a quiz, and the raw scores are 20, 18, 15, 12, 11, and 10. And what we want to do is take those scores and change them to percentages. So we're going to transform them by taking the score and dividing by 20, because the possible number you could get on this right was 20. And then you multiply that by 100, and you should get the percent. So like I could take 20 divided by 20, multiply by 100, and a person would end up with 100%. 18 out of 20 times 100 is 90, and so on. So now what I've done is I've taken all of these 6 raw scores and transformed them to percentages. And this is an example of a linear transformation. How I know that it's a linear transformation is if I go ahead and plot the raw score, like here on the x-axis, against the new percentage score, and you see all of those dots there. Those dots represent the 6 scores on the quiz. So you can see each person's score, what their raw score was on the x-axis, and you can also see their corresponding percentage. And you can see that they're all on the same line. That is a linear transformation because all I did in my transformation is just change what the units were, didn't change anything about the shape of the distribution. So linear transformations don't change the shape of the distribution, but they can change the value for the mean, the median, the mode, etc. And so that's partly why we perform such linear transformations. Now, back to z-scores. A z-score is defined as being the number of standard deviations a score is above or below the mean. So this is really the units for a z-score, is standard deviation units. A z-score that has a value of 0 is equal to the mean for that variable. So that means that it's not above or below the mean. It is exactly at the mean. So z-scores are simply a transformation of a raw score into a score that is standardized. That is, once you've converted this thing into this new z-score, you can now use the z-scores to compare between different variables because they're all on the same unit of standard deviation units. Now, we'll come back to this point again, but let's first of all just look what the formula is for a z-score. So the way you can get a z-score is you're going to take each score, which is the x in this formula, and subtract the mean from it. So you have to know the mean, and you have to also know the standard deviation. So you're going to take each person's x, subtract the mean, do that in the numerator, and then divide that by the standard deviation. So take the x, subtract the mean from it, then divide by the standard deviation. That is what a z-score is. So all you have to do is take any one person's x, subtract the mean, divide it by the standard deviation. You now have their z-score. It's like going from the raw quiz score to a percentage. This time we're going from a raw score to a z-score. Normally, when you perform a transformation, you do it to all of the scores that you have. So you're going to convert every single score that's observed to a z-score. And then you could look at for instance, the frequency distribution that you get, the histogram. So for instance, here I've got an original set of raw scores that look like a bell-shaped curve, sort of. They have a mean of 20, and they have a standard deviation of 1.5. Okay, so that's the example. Now, if I have somebody who has a score of 30, what would their z-score be? Well, I've just showed you the formula for a z-score. It's going to be that I'm going to take that person's x, their 30, and subtract the mean from it, and then divide by the standard deviation. So in this case, I can see that I'm going to plug in 30 for the x. The mean was given as 20 for this distribution, and the standard deviation for the distribution was 1.5. So I've taken that person's x, 30, converted it to 10 over 1.5, or the value 6.67. So they now have a z-score that's 6.67. And if you look in my little picture here, you can see there's a red arrow off to the right. That's approximately where somebody would have a z-score of 6.67 or have a raw score of 30. They're very far away from the mean. They're 6.67 standard deviations away from the mean. What about if someone had a score of 18.5? How would we compute their z-score? So think about that for a moment. The x is 18.5. We have the same mean, 20, the same standard deviation, 1.5. So we're going to plug this into our formula for the z-score, x minus the mean over the standard deviation. That gives us 18.5 minus 20. Divide that by 1.5, so we're going to get minus 1.5 over 1.5. That ends up giving us a z-score of minus 1. So you remember, minus 1, that's in standard deviation units. That tells us that this person's raw score is 1 standard deviation below the mean of the raw scores. And you can see there that I've drawn a little red arrow. That's just 1 standard deviation below where a person who had a score of 18.5 would be. There'd be 1 standard deviation away from the mean. So that is how z-scores would be computed for just 2 scores. But as I said, what you normally do is you take all of the scores in the distribution and you repeat this. So you take every single raw x score that you get and you create a new distribution that's made up of only z-scores. So you could take 30 x's that you had, all of your original raw scores, and convert them to 30 z-scores. If you had 2,000 original scores, you can convert all 2,000 of them to z-scores. And then you could look at their distributions. You could look at the distribution of the z-scores. And z-score distributions, because they're standardized, have some interesting facts about them. So here's some important facts about z-score distributions. It turns out that once you converted all of the raw scores, transformed them to z-scores, that the mean of all of those z-scores in any distribution is always 0. So it's defined as always having the mean of 0. Take all the z-scores, take all the raw scores, convert them to z-scores, and you'll see that the mean of all those z-scores is always 0. The standard deviation of all the z-scores in a distribution is always 1. So that's another important property of z-score distributions. They always have this property that their standard deviation is 1. And finally, the third kind of important fact about z-score distributions is that the shape of the distribution of z-scores is identical in shape to the distribution of the original raw scores. So nothing has changed about the shape. It's just the mean and the standard deviation that's changed once we've changed everything to z-scores. All right? So take those 3 facts and let me try to show you some examples to convince you of this. So here is an example of a z-score transformation of an entire distribution of scores. Up on the top we have their raw scores, and the raw scores had a mean of 120 and the standard deviation was 30. Then every score on the top was changed to a z-score by using the formula. And on the bottom, what we've done is we've plotted the distribution of all the z-scores. We basically have created a histogram of all of those z-scores. And you'll see now that the mean of all those z-scores is 0 and the standard deviation is 1. Those are the first 2 facts I mentioned, that they're always true, that you're always going to find that the mean of a distribution of z-scores is 0 and the standard deviation is always 1. But the other third important fact is to notice that the shape of the distributions is identical. Nothing's changed about the shape. This would even hold if we had a completely different shape, a narrower distribution. So this one only has a standard deviation of 10 on the right. So it still has a mean, this one has a mean of 90 and has a narrower distribution. But you can see that the resulting z-score distribution below it is again having a mean of 0 and a standard deviation of 1, but it has done nothing to the shape. The shape is still that same narrow looking shape that it had when it was the raw scores. So that's important to remember, that we're always just converting things to z-scores that we're going to get the mean of 0 and a standard deviation of 1, but it's not going to change the shape. Now remember that I told you that once you've transformed things to z-scores, you can now make meaningful comparisons between the different scores that come from different populations or even different measures. There's something sort of universally translatable about z-scores, that once any variable that you have out there has been transformed to z-scores, and you look at a person's z-score instead of their raw score, you can make all sorts of comparisons, even if they come from different populations and even if they come on different measures. Let me show you how that works. So here's an example where 6 months after a divorce, a former wife and a husband each take a test that measures their adjustment for divorce. The wife has a score of 63 and the husband has a score of 59. Overall, what we know about the population of men and women who've gone through divorce is that the mean score for divorced women on this test is 60, with a standard deviation of 6, whereas the mean score for divorced men on this score is 55, and the standard deviation is 4. So the question is that given the fact that men and women differ already on this test, which of the two here has adjusted better to the divorce in relation to other divorced people of the same gender? So what this is trying to get at is that we have really actually different population means for women and men and different standard deviations. So a person who has a score for a woman who has a score is being compared against other women. Men would be compared to other men. So if we want to know how this man and this woman are doing relative to their gender, the only way we can make a meaningful comparison is if we convert both of their raw scores to z-scores. And we're going to do that by using their population's respective mean and standard deviation. So what I have here is worked out this particular problem solution. So up at the top, I've got the wife's X is 63. Her population mean for women is 60 on the test with a standard deviation of 6. For the husband, he had an X score of 59, but he comes from a population that has a mean of 55, and the population standard deviation is 4. So as I said, we need to transform those X's to Z-scores to see who's higher based on their Z-scores. So when we're computing the wife, there's our formula for the Z-score. I'm going to plug in her X, which is 63, subtract it from 60, that's the mean, and then divide it by the standard deviation, which is 6. So I get 3 over 6, or 0.5. So she's a half a standard deviation above the mean for her gender. For the husband, you can see that once we convert his X to a Z-score, that means we're going to plug in 59. The mean is 55 for men. The population standard deviation is 4. So that ends up giving us 4 over 4, or 1. So the husband's transformed Z-score is 1. That means he's 1 entire standard deviation above the mean, whereas the wife is only a half a standard deviation above the mean, 0.5. So in fact, the man is doing better than the woman because his score is higher above the mean than the woman is. So he has adjusted better, even though his raw score was lower than the wife's score. And again, this is all because we're computing a Z-score to make a meaningful comparison between the two different populations. Now, another thing you can do is that if you have a Z-score, you can convert from Z-scores back to raw scores. So here's that formula for a Z-score, X minus the mean over the standard deviation. But with a little algebraic manipulation here, you can also make that so that we are solving for X. So now it says that X is equal to the Z-score times the standard deviation plus the mean. So if I know the Z-score and I know the mean and the standard deviation, I can plug them in over on the right side and I can figure out what that Z-score's actual raw X is. So it's just going backwards. So if we had the X, we converted it to a Z. Now we want to take a Z and convert it back to an X. And we use the formula here on the bottom. So in our example problem here, I've given you on a particular intelligence test, the mean number of items correct is 231 and the standard deviation is 41. So you can see then we have a mean of 231, that standard deviation is 41, and it says what are the actual or raw scores on this test for people with IQs of 107, 83, and 100. And it says that IQ is set up to have a mean of 100 and a standard deviation of 16. So what this is trying to do is saying, okay, I've measured intelligence with this new test, where that test has a mean of 231 and a standard deviation of 41. And I can get these raw scores for those people, but I only know their IQs. So I happen to know that this person has an IQ of 107, another person has an IQ of 83, and so on. And so if I know what a person's IQ score is, can I then convert it to what their score would be on this new intelligence test that has a mean of 231 and a standard deviation of 41? So in order to solve this problem, what we're going to do is we're going to take those three IQ scores and convert them first to Z scores. And then once we have them in Z score language, we can convert the Z scores to raw scores on the new intelligence test. So that's the logic behind this. So in this problem, we first have to convert each IQ score to a Z score. Then we're going to convert the Z score to scores on the, on the new intelligence test. Okay, so on this test that we just made up. So we're going to transform each X to Z scores. So for the problem A, what we're going to do is take the Z for that first person had an IQ of 107. So we plug in 107 for the X, the mean is 100, and we're going to say on this IQ test that IQ is 16 for a standard deviation. That would mean that a person who had a score of 107 would have a Z score of 0.44. For B, that was a person who had an IQ of 83. That's below the mean, so we have 83 minus 100 over 16. That reduces down to minus 1.06. So they're 1.06 standard deviations below the mean if they have a score, an IQ of 83. For problem C, we had somebody who had an IQ of 100. The mean of the IQ score is 100. So we have 100 minus 100 over 16, and that would then convert to a Z score of 0, because remember, a Z score of 0 is actually at the mean. Now that I know their Z scores on intelligence on an IQ test, if I want to now figure out what their scores would be like on this original new intelligence test that I've invented, what I'm going to do then is take their Z scores and convert them to X scores on the new test. So I'm going to use the mean and the standard deviation that were given in the problem for that new test, this original test. And the mean for that test is 231. The standard deviation is 41. So all I have to do now is plug in the Z scores that I computed on my previous step. So I have a 0.44 Z score, multiply that by a standard deviation of 41 and add 231, and that gives us an X then of 249.04. For problem B, we plug in minus 1.06 for the Z score, multiply it by 41, add 231 to it, and we get a new score of 187.54. And then for problem C, we have 0 times 41, add that to 231, and we're at 231. Now think about that last one. It's probably the easiest one to understand. There was somebody who had average intelligence. They had 100 on the IQ test, which is the mean on the IQ test. So that would mean that on this new test, this new original test that's been invented, they would also have the mean. They would have a mean, and the mean here was 231. So that's why their IQ of 100 converts to 231 on this new test. So these are just examples of how we can go back and forth from X to Z and Z to X. Of course, in the book, they've got more problems worked out. You could try the practice problems in set 1, and then also you've got some problems that will be assigned for your problem set A that involve converting Z and X scores. So that's all I have to say for now on Z scores. Let's go to the second part of today's lecture, which is on the normal distribution. Now, we've actually been talking about the normal distribution in previous weeks. We've been talking about this thing that looks like a bell-shaped curve. There's our bell. There's actually an equation that defines what a normal distribution is, and that's what it is. That's the thing that appears here in the bottom of this slide. That's how you know, that's the function for creating a normal curve. A true normal curve, by the way, has these two tails going off to the left and the right, but they asymptote. They never actually touch the x-axis, so they forever get closer and closer without touching the x-axis. And that's defined, like I said, by this function that you see at the bottom. Now, we really like normal distributions. They're very important in psychology. And so that would lead us to this question: why is the normal distribution important? Well, I have two main answers to that question. One answer is that many variables naturally occur as normal distributions in psychology. So it turns out that many biological variables, for example, things like height, heart rate, etc., that when you take a large number of people, look at their heights, look at their weights, look at their heart rates, you'll see that those variables are distributed in a normal curve. That many psychological variables also appear as normal curves in nature. So IQ tends to be normally distributed. Many personality factors that we can measure about people are normally distributed. So it turns out that just in nature, a lot of things actually occur as normal distributions, which is quite handy given the fact that so much of what we're going to be doing then in psychology also has normal curves, and we can use some of the properties then of normal distributions as we conduct our statistics. So, in fact, the second main reason then why we're interested in the normal distribution is that many inferential statistical methods that we've developed over the last 100 years were developed assuming that the population for the variable that you're interested in is normally distributed. So we just assume right off the bat that this thing that we're studying has a normal distribution. Now that might be erroneous. It might be wrong that some things are not actually normally distributed, but it works for the most part for most things. All right. So those are the two main reasons why we use the normal distribution. Now, a special version of the normal distribution is one that's been standardized, where we've changed it so that we are using z-scores. So you can see the way I've drawn this one is this normal distribution has a mean of 0 and has a standard deviation of 1. And I've marked off 1 standard deviations, 2 standard deviations, and 3 standard deviations above the mean and 3 below the mean. I've also indicated here with these symbols that the standard deviation of this particular distribution looks like that. It's the Greek symbol for sigma. And then mu is the parameter for the population mean. Okay, so that's what you'll keep seeing here, but that's basically talking about a mean and a standard deviation. Now, there's some special characteristics about normal curves when you think about their means and their standard deviations. So it turns out, for instance, that the inflection point of a normal curve, this part on the right side or the part on the left side, where it goes from a concave curve to a convex, kind of changes its direction, that point is called an inflection point, and it's exactly at 1 standard deviation above and 1 standard deviation below the mean. That's what's true always about normal curves, that they have that property. So 1 standard deviation above and 1 standard deviation below the mean is where those inflection points are. Another thing you can think about is what proportion of all of the scores that are in a distribution are in a normal curve. Now, the easy thing is to say is that 100% of all of the scores are within what I have shaded in red here. So all of the scores in a normal distribution are in the entire distribution. Or instead of a percentage and saying 100%, I can use a proportion and say that 1.00 of the entire distribution is in the entire distribution there in red. But now let's go ahead and cut up some pieces here and look at some things about the proportions that you see there. So here, what I've done is I've marked off 1 standard deviation above the mean of 0 and 1 standard deviation below the mean. And you can see that in red, what proportion of the entire curve is between -1 standard deviation and +1 standard deviation. And that turns out to be always the case, 0.683. So 68.3%, or the proportion 0.683, of a distribution is always between -1 standard deviation and +1 standard deviation when it's a normal curve. Or when we look at 2 standard deviations above and below the mean, you can see that our proportion is now 0.954. So really, once we get 2 standard deviations away, above and below, we're covering up most of the graph, most of the figure of a normal curve, and counts for most of our scores. So now 95.4%, or 0.954 of the distribution, is between -2 and +2 standard deviations. When we go all the way out to 3 standard deviations, we pretty much have covered the entire curve. In fact, you can see now in red that we have 0.997 of the distribution. There's very little left over. And that's the little bit that's left over above and beyond 3 standard deviations, is that little part of the tail that forever asymptotes closer and closer to the x-axis without touching it. But really, once we get to 3 standard deviations in a normal curve, we're really talking about almost the entire curve. Everything has been accounted for once we get to 3 standard deviations away. So in fact, we have kind of a handy rule here that we can call the 68, 95, 99.7 rule, that for normal distributions, 68% of the values are going to be between +1 and -1 standard deviations from the mean, that 95% of those values are between +2 and -2 standard deviations from the mean, and that 99.7% of our values, our scores, are between +3 and -3 standard deviations from the mean. So that's always true about normal distributions. It's not true about things that deviate from a normal distribution. Now, we were always talking about the things that were between two markers, between +or -1, or between +or -2 standard deviations. But don't forget about the leftovers. There's also stuff that's outside the markers. And so you can see here, for instance, that excuse me, when I've marked off plus and -1 standard deviation, I still have 0.159 of the curve left over above 1 standard deviation and 0.159 left over below -1 standard deviation. And if I add those two parts up, the two parts that are in red there, that would be 0.318 of the entire distribution, or outside of those markers. When I go to 2 standard deviations away from the mean, what I have left over in red is only 0.023 above and 0.023 in the bottom. Add them together, it's 0.046. So only 0.046 of a distribution are above and below 2 standard deviations from the mean. And when we get to 3 standard deviations, or hardly anything left over, as I said, excuse me, it's only 0.001. And so you can see that we have 0.001 above, 0.001 below, add them together, and only 0.002 of the distribution is outside 3 standard deviation markers. Another thing we can do with these distributions is that we can also look at what's above or below a single point. So if I, for instance, just mark off right in the middle of the distribution at the mean, that means that above that point is 0.5 of the distribution, and below that is 0.5 of the distribution. So here at the mean, half of the population is below and half the population is above, right? If I go to another point, I drag it up here to 1 standard deviation above, you can see that at that point, 0.84 of the population is at or below the value. So I've cut off 0.841 in red, and then I have the remainder still left in blue. I don't even have to use whole numbers here. I could go to, for instance, -2.4 standard deviations below the mean, and the only thing that would be below that is 0.007 of the population. So that's another great characteristic about normal curves, since they have this exact shape and these exact characteristics, that once you convert things to a z-score, for instance, and find out how many standard deviations away something is, you now have an accurate measure of what proportion of the population is at or below a certain point in the distribution. So really, what standardized normal distributions are a distribution of z-scores. And so instead of saying -1 standard deviation, -2 standard deviations, I could say I have a z-score of -1, -2, -3, and so on. Now, you'll see that if you look in your text at the end of this chapter, that there's an appendix in the chapter. It's at the end of the chapter. It's not the end of the book. So it's on pages 114 and 117. And what this appendix does is it shows you the proportions, or in this case, it actually uses percentages of the scores that would be between the mean and the z, or what's left over in the tail. And once you have that kind of information, then you can go ahead and figure out a lot of things about different characteristics. Oops, and now I'm going to interrupt this lecture. I'm recording this message a while later after I changed textbooks for this course. And so you'll notice now that in my lecture, I do keep referring to a table in Appendix A and on different pages that are in the different textbook that I was using at that time. Everything works pretty well, pretty much the same for this lecture, using the Haslam and McCarty textbook instead. And so I want to go ahead and just quickly show you how Appendix B and Table B.1 is used to do the same kinds of problems I'm going to talk about in the next few slides. So when you're using the Haslam and McCarty textbook, look to Appendix B in the back of the book. In Appendix B in the back of the book, there's a Table B.1. Now, Table B.1 looks like this, and it's spread across 3 different pages. Unfortunately, they didn't do a very good job of making these headings and the columns going down actually go across the pages very well. So you're going to get a little confused when you look across the 3 pages when you're trying to find certain numbers, just because of the way they didn't actually very carefully organize this table. But still, we can make sense of it. And the thing that you need to notice is that there are actually 3 columns that are being repeated on each page 3 times. So here's the first 3 columns. You can see the first column's got a Z column, then an area in the body below the Z, an area in the tail beyond the Z. And it goes all the way down, and you keep changing different values there for the Z. And then you'll see that in the middle 3 columns, there's also a Z column, an area body and body below Z, and the area in the tail beyond the Z. And finally, there's a column Z, area in the body below Z, and area in the tail beyond Z. And you can see there's different Z values there. So if it helps you at all, you might want to go ahead and draw a line separating those 3 columns. I found it a little confusing sometimes when I've been looking at this appendix trying to find values. But they're all there, just not the best organization or representation of the values in table B.1. So how do you use this? Well, if you look at, again, these 3 columns that get repeated, the Z score, and then the area in the body below the Z, and the area in the tail beyond the Z. The area in the body below the Z, basically that corresponds to what I have on my curve there in red. So the area in red would be the area in the body below the Z. The line that's going down to like 1 standard deviation above the mean, that would be the Z score right there. And so below there, the body below there is the part in red. And then the part that's in the tail beyond the Z would be the part that's in blue. Okay? So the area in the tail beyond Z is the blue part. All right. Now, how do we actually figure out where the Z score is? Because I have a line there marked where 1 standard deviation above the mean is, and I'm saying that the area that's in red is 0.841. Well, what I would do is just look down this column here until I got to area in the body below the Z, and there you can see I find 0.841, right? So there's the red part, 0.841, and then I can look to see what the Z score would be, and it's 1. So a Z score of +1 is above the mean. It's that mark there at between the blue and the red in my little curve. And then if I look to the right, the area in the tail beyond the Z, that's the part in blue. And so that's 0.159. And if I add 0.841 to 1.59, I'm going to end up with 1.0. And so I've then accounted for the entire area under the curve. So that's basically how it works. You just need to keep looking at these 3, Z, the area in the body below the Z, and the area in the tail and beyond Z. And you'll see that in the lecture, in the next few minutes, that it corresponds and lines up really well with exactly these 3 columns. So now back to your regularly scheduled lecture. So if you translate your raw scores to Z scores, and you believe that your population is normally distributed, you can then determine what proportion or percentage of the population is above or below any particular raw score. So, for instance, let's say you take your pulse and you just go ahead and record your pulse. You can just do this right now while you're listening to this lecture. Just put your fingertips on your pulse there on your wrist and see if you can feel your pulse. And what we're going to do is I want to count off 15 seconds starting now. Stop. Now take that number that you just counted of your pulse and multiply it by 4, and that will be your resting pulse. Now if that didn't work, go back and hit rewind and try to get your resting pulse. So just do it for 15 seconds, take whatever number it is that you counted, multiply it by 4, and now you know your pulse. Now let's say that my pulse is 80, okay? So is that good or bad? If I have a pulse of 80, how do I know how well I am compared to other people? So what you want to do is take your pulse and convert it to a Z score, and that will help you then figure out what percentage of the population is above or below your particular pulse. Now it turns out that in a population of normal, healthy adults, that the mean of pulse rates is 73. So 73 is a very average population mean for pulse, and the standard deviation is 8. So what you see that I've done here is I've taken my score of 80, that was my X, And I've subtracted the mean that I just gave you, which is 73. And then I divided it by the standard deviation, which was 8. So now I have 80 minus 73 over 8, or 7 over 8. And that gives me then 0.88 as my z-score, right? So I've got 0.88 as a z-score. And so that would be what my z-score is after I've converted my raw score of 80. Try to do that for yours now. Go ahead and see if you can compute your z-score based on the pulse that you computed. Now, once you have that z-score, we'll continue here. And you can go ahead and now look in Appendix A. And you're going to specifically look at what's called this table A1, the normal curve areas. And you want to find your z-score. So go down the columns on that table to find your z-score. And then if you look in the second column that's been labeled percent mean to the z, that will tell you then what percentage of people have your score from the mean to the z. Now, for me, that z-score I had was 0.88, which if you look in the table, you'll see that 0.88, the percent mean to the z, is 31.06. Now, I'm above the mean. I have a positive z-score, so that means I also have to consider all the scores that are below the mean, and that's 50%. So if I add these two pieces together, the part that's between the mean and the z-score, which is 31.06%, you can see it shaded in the picture in table A.1, and add that to the 50% that are below the mean, that would mean then that my z-score, 0.88, is where 81.06% of this distribution is below that score. So that means that 81.06% have a pulse that is less than mine. So I have a pretty high pulse then compared to everybody else. Again, you can do this yourself by looking at the picture there and see if you can figure out. Now, if you're below the mean, if you have a pulse that's below the mean, you're going to have a z-score then that goes below the mean. It's negative. Just still use the z-score absolute value here in column A. And just remember then that you don't need to add 50%. What you're going to do is actually take your percentage that you get from the z-score, from the mean to the z-score, and subtract it from 50%. And that will tell you what's left over, what people are below that particular score. Now, in my case, we're just going to stick to having a z-score where I end up having 81.06%. You can see there's my 0.31 that goes up to a z-score of 0.88. And then I have 0.50 is all that stuff that's from the mean below. I've added them together, and that means that 81.06% have a lower pulse. That also could be asked differently. We could say, what about the people above my pulse? That's that part there on the right. And so I want to take my 0.81 and just subtract it from 1, and that would tell me the percentage or the proportion of people who have a score above my pulse. In my case, that's 100 minus 81.06%. That would mean that 18.94% of the population have pulse rates higher than mine. So when in doubt, always try to graph these z-scores so you can keep in mind if your z-score is negative, that means it's below the mean. If it's positive, it's above the mean. And you want to kind of get an idea how far away from the mean it is and so on. So that all that will help you to kind of solve the problem that you're doing when you're looking at these z-scores. Now, if you are starting with a percentage, like in fact you have this one, what pulse rate represents where 75% of the population is below it? That means I want to take this percentage information and convert it to a z-score, and then convert the z-score to an x. So if I break this problem up, it's saying, where's the place that 75% of the distribution is below me? Well, I've marked off 75%. So I've got the 0.5 of the bottom half of the distribution below the mean. Plus I got 0.25 yet, that's above the mean. And then I've drawn a little arrow to say, okay, this is approximately where I think the z-score would be. But in order to find that, then I'm going to look on my table in A.1 where the percent mean to the z is close to 0.25. I want to find the value that's 25%. And if I do that, then, and I find this place where that is, that's actually a z-score of 0.68. So the closest value that you can see when you look at table A1 to 25% is 0.68, which is actually where 25.17% is. Close enough, that's the closest value I can get. So I'm going to use my z-score or a z-score of 0.68 and say that's the place where 75% of the population is below it. But the question actually asks, what's the pulse rate that represents where 75% of the population is below it? And that means I need to take my z-score, which is in the standardized unit fashion, and change it to a raw score. And in order to do that, I have to go back to the problem that said what's the mean and the standard deviation here. So the mean of pulse rates is 73, the standard deviation is 8. So I can go ahead and plug in to try to find my x, my pulse rate here. Take the z-score of 0.68, multiply it by 8, the standard deviation, add the mean to it, that's 73, and I end up getting an x of 78.44. So the answer, ultimately here, the pulse rate that represents where 75% of the population is below it, is 78.44. And again, if I graph this problem, you can see there's where 78.44 is. It's above the mean, and it's the place where 0.75 of the entire distribution is below that point to the left. Okay? The little 0.68 I have down there at the bottom is the z-score that I computed. So that just gives you a flavor of some of the things you can do with a normal curve. Now it's time to move to the third part of this lecture. And what I want you to do as we start to think about probability is just to think a little bit about these distributions I've been showing you. If you really look at it and you think about it, that a population frequency distribution actually gives us exact information about a distribution of scores. And when I talk about the proportion of scores and say 0.5 is below the mean and 0.5 is above the mean, that would mean then that I can turn this into a probability estimate. I can go ahead and figure out what the chances of picking somebody out of this population would be that they were above the mean or below the mean. So if I randomly choose one person out of this population, I just grab a number out of the hat, I could figure out that 0.5 of the population, I would have a 0.5 probability they'd be below the mean, and 0.5 would be that they'd be above the mean. So I really have some probability information here based on this normal distribution. If I make this a little bit more complicated, I could say, okay, what if I randomly pick somebody who has a score? What would the probability be of getting somebody who has a score between a z-score of minus 0.5 and a z-score of 0? The answer would be 0.21. So you see that 0.21 marks off where we have a z-score of minus 0.55 and a z-score of 0. So a z-score of 0 is right in the middle of the distribution, so that's the probability, 0.21. If I ask what's the probability of getting a score below a z-score of minus 0.55, that's everything to the bottom of it, the 0.29, the tail going off to the left. So the probability of getting a score just by chance that's below minus 0.55 is 0.29. And finally, a probability of a score above a z-score of minus 0.55, I need to add everything that's above that place, so that's 0.21 and 0.50. That means then the probability would be 0.71. So these proportions that we keep talking about here can actually be converted to probabilities. And that leads us then to talk about probability. And the point here today is just to get you introduced to it. It's talked about again in the book some more, and it even gets into some more advanced topics of probability that you should to look at and try to get your head around. Basically, the formal definition of probability is the expected relative frequency of a particular outcome. Okay, so it's a relative frequency of a particular outcome. That means it's going to be in proportions. It's going to have numbers like 0.99 or 0.24. And in order to show what something is in terms of a probability, we use this italicized p as the symbol for probability. And so that's where we get something like, what does the p less than 0.05 mean? It means that the probability of getting this thing happens less than 0.05 at the time. What does it mean, though, when you have a probability of 1? Well, a probability of 1, if you think about it, means that it's guaranteed to happen. It's covering everything. If probability of 1.0 means it's going to definitely happen. What about this? What about when you have a probability of minus 0.4? Well, that's not some sort of weird alternate universe. It turns out that there is no such thing as a probability of minus 0.4. It's nonsense. Probabilities can only have values from 0 to plus 1. So they have to be somewhere from 0 to plus 1. So again, if we go back to this question of let's pick someone randomly from a population, and I say what's the probability that we'll pick somebody who has a z-score greater than minus 0.55 or greater than 0, what I would do then is look at the different proportions that I have here. So it says who has a z-score greater than minus 0.55, so that's everything of 0.21 and 0.5, or greater than 0, and I go ahead and figure that out, that's 0.50. And I can start to get an idea then of the probabilities of getting different kinds of scores. Or if I pick two people, I could say, what's the probability that we'll pick someone who has a z-score greater than minus 0.5 and a person who has a z-score greater than 0? So again, you can determine probability questions like that from looking at the proportions in the normal curve. So again, that leads us to statistical inference. We're going to start talking more about probabilities because we use these probabilities to test the likelihood of our hypotheses. And just to reiterate that again, a probability of 1 means that it's certain to happen. It's a 100% chance. 0.5 would mean it's only got about a 50% chance. So that means like it happens half the time. For instance, when you flip a coin, the fact that you're going to get heads is about 50% of the time. 0.167 means that it's going to occur once in 6 times, or 16.7. So this is like rolling a 1 on a die. Or a probability of 0 means that it's absolutely never going to occur. That's what a probability of 0 means, 0% chance of it happening. Now, I want you to think kind of philosophically a little bit about probabilities. And imagine that I present you a coin and ask you to judge whether it's a fair coin or not. So I give you this coin, and I say, is this a fair coin? Now, fair means that it should have about an equal chance of getting heads or tails, right? So you get a probability of heads would be 0.5, a probability of tails would be 0.5. And so the question then is, how many consecutive times getting heads would you need to see before you would determine that a coin wasn't fair? So if I kept flipping a coin, and it said heads, and I flip it again, it says heads, and I flip it again, it says heads, you might right there say, well, yeah, that could happen just by chance. But let's say I keep doing that. How many times would you have to do this before you'd start to get suspicious? Well, in the movie Rosencrantz and Guildenstern Are Dead, you can see this is a movie that came out like 20 years ago. They have an opening scene in which this actually happens. Now, Rosencrantz and Guildenstern are two minor characters, I think, in Hamlet in Shakespeare. And in this movie, they've been elevated to the main characters of the movie. So they happen to just kind of walk in and out of Hamlet in the background, but you'll see that it's really a story about Rosencrantz and Guildenstern, these two minor characters. And at the beginning of this, you can see what happens.
Heads. 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 Bet. Heads I win. Bet. Heads I win. Again. Heads. Again. Heads. 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 Whoops. Whoops.
must be indicative of something besides the redistribution of wealth. It must be indicative of something besides the redistribution of wealth.
Heads.
A weaker man might be moved to re-examine his faith.
Heads.
If in nothing else, at least in the law of probability.
Examine his faith. Heads.
If in nothing else, at least in the law of probability.
Heads.
Consider. 1. Probability is a factor which operates within natural forces. 2. Probability is not operating as a factor. 3. We are now held within sub, or supernatural forces.
Sub or
Discuss.
supernatural forces. What?
Look at it this way.
Discuss.
If 6 monkeys...
Look at it this way.
If 6 monkeys... The law of averages, if I've got this right, means that if 6 monkeys were thrown up in the air long enough,
The law of averages.
they would land on their tails
That if 6
about
monkeys
as often as they would land on their...
heads. They would land on their tail.
Getting a bit of a bore,
They would
isn't
land
it?
on their head.
A bore?
Well, the ball.
What about the suspense?
The ball. Well,
What suspense?
what about the suspense?
It must be the law of diminishing returns.
What's suspense?
I feel the spell about to be
The law
broken.
of diminishing returns. I feel the spell about to be broken.
Well, there's an even chance.
Well,
78 in a row.
A new record, I imagine.
78 in a row.
Is that what
A
you
new record, I
imagine?
imagine.
A new record?
is that what you
Well,
imagine?
No questions, not a flicker of doubt.
I could be wrong.
Not a flicker of doubt.
No fear?
I could be wrong.
No fear.
Fear.
79.
So the question bothering these guys is that how many times do you throw heads before you start to think that maybe there's something mysterious or magical going on? The question is, though, is it really possible that you could have that many times in a row that you could actually get heads? It is possible. So it's not impossible to have 79 or 80 throws of your coin and get heads. It's just that it's very unlikely. But it's probably unlikely enough that you start to infer that your coin is not fair. That's the issue here, because you're starting to get suspicious because you're thinking, okay, it's not impossible, but the chances of getting heads that often is very unlikely. And so that makes you start to doubt things, right? Doubt the coin is actually fair. So that actually is kind of where we come with this probability of less than 0.05. So these are all these other probabilities we're talking about, but the scientific convention, the one that we use in psychology usually, is a probability of less than 0.05, where we start to say, if something happens that rarely, we think that the way that things are described normally are not so. So again, it's not saying it's impossible, but it's saying that this particular event is happening less than 5% of the time, and it makes us question then whether or not our initial assumptions about whatever it is that we're testing are actually valid. So we'll come back to that because we're going to be covering this issue of sampling and probabilities as we continue on for the next couple of weeks. I do want to just finish today by talking about sampling and probability in terms of what it means when we're sampling from a population. Because as you know, we draw samples from populations and then make inferences about the populations based on our samples. So we need to talk about what actually random sampling is. So random sampling means that I'm going to go ahead and draw people out of this population at chance. I just randomly pick them. And it means that everybody in the population had an equal chance of being picked, and they become a member of my sample. So that is what random selection is. Random selection means that we create a sample from the population such that each individual has an equal and independent opportunity to be selected. So every time I do this, everybody had a chance to be picked. There's no way that you couldn't have a chance of being picked. So that's what we mean by a random selection. If you think about it, again, the way that we test participants here at UQ, if we say you guys represent the population, are we randomly selecting the students who are taking 10, 20, and 10, 30 when we test them in our studies? No, because not everybody has an equal chance. It's actually based on the time of day that the studies are available, which day of the week it is, whether or not you're even on campus. So a true random selection would mean that everybody had an equal chance of being picked. And so that's a very precise definition of a random selection. All right, so we've covered a lot of topics in this lecture. And again, it's going to be important that you also review these in the book. You go back through, answer some of the practice questions there, try to summarize things before you go ahead and take the quiz, because it's going to become more difficult again each week as we cover new material. So we've covered how Z-scores are a special type of transformation that lets us compare things because the Z-scores are standardized. That we also learned about normal distributions this lecture and why they're special and important to us in psychology. And we've now introduced this topic of probability that we'll return to in the next few weeks. So that's all I have for today.